This is the first of 4 videos on SLO 8, confidence intervals. We're going to start with section 8.1. Today what we're going to be doing is a somewhat unrealistic procedure for a somewhat unrealistic situation, I suppose, where we're trying to estimate the population mean, but we somehow know the population standard deviation. That said, it's almost completely analogous to what we're going to do in the next section, where we don't know the standard deviation of the population. So it's good to have this foundation. Anyway, let's consider example 1 right here, right? Where we're trying to estimate battery life, the average battery life for a Lenovo IdeaPad, right? It's a type of laptop, right? I made up these numbers, right? Don't sue me, Lenovo, right? Suppose we sample 81 laptops. Mean battery life is 7.3 hours. And suppose that we somehow know that the standard deviation of IdeaPad batteries in general, their battery life is 0.6 hours, right? So just to review, we know the population standard deviation is 0.6 hours, but we're not sure what the mean battery life is. So we sample 81 of them, and we get a battery life of 7.3 hours, okay? So then the question is, do we believe the mean battery life for all IdeaPads is 7.3 hours? And you know, maybe, roughly. And the question is, well, maybe is it 7.2 hours, 7.4 hours, 7 hours, 8 hours, right? Maybe in the range of, I don't know, like 7, maybe I'll just write like 7 to 7.6 hours, right? We're really not sure. Right? We can guess, but we're not sure yet, right? And that's why we invent confidence intervals, right? So what we're going to do is we're just going to say, consider the sample mean, which is also called the point estimate, but calls it the point estimate. And sample size. Create a confidence interval. Excuse me. Create a confidence interval of likely range of possible population means. All right, and that's what we're gonna do. That's our approach. So let's be formal about this. Let's recall that by the central limit theorem, for large samples, which means n is greater than 30, the sampling distribution is approximately normally distributed. Regardless of whether the variable's distribution is normal, right? If the sample size is small and the variable is normal, then the sampling distribution is automatically normal. Anyway, we also know that the standard error, which remember we denote as sigma sub x bar, is sigma x bar equals sigma over root n. Okay? So then what we do, we're going to combine this with our understanding of z-scores. And what we can do is we can use confidence intervals to get this meaningful interval around our point estimate or sample mean. Now, suppose we want to be, 95% confident. This is probably the most common level of confidence that you're going to see. Which means that if we were to do this experiment, right, this random sample over and over again, and get various sample means, 95% of the time, the true population mean would be within our confidence interval. Even if our sample means, or point estimates, as the book likes to call them, differed. So here's how we're going to proceed. Now, I'm going to do a slightly more drawn-out procedure for what we're going to do sometimes, because sometimes you can use Minitab to skip a couple of steps, but we have to understand concepts first. We have to understand the whole process. First off, we're going to find the standard error, which by the central limit theorem is population standard deviation over root n. Remember, we're assuming unrealistically that we know what the population standard deviation is. Then we're going to decide the appropriate level of confidence, often 95%. Now, you're also going to see a variable alpha pop up sometime. Just going to put this in red. You can feel free to ignore this, but if you want, you can look at the book and see what I mean by 1 minus alpha. That scares you, Greek letters scare you, just ignore it for now. Okay? So use Minitab to find the corresponding z-score for the confidence level. Then we're going to find the margin of error, which we're going to abbreviate with MOE. MOE is going to equal our special z-score, which the book and I denote as z sub alpha over 2. You can check the book to see why that's the notation, times our standard error, which we know is sigma over root n. And maybe I ought to lift that up a little bit. There you go. Okay? And then the interval x bar minus the margin of error to the x bar plus the margin of error, right? Remember this parentheses notation for an open interval is our, in this case, 95% confidence interval. Or I might just abbreviate it as a CI. Which means we are, and this is precise language that you should use if we ever ask you a question like this. We are 95% confident that the true mean is within the interval. In other words, if we sampled another 81 ideopeds repeatedly, then 95% of our samples should contain the population mean battery life, which we just call mu, right? So that's what we do. So let's actually do this out then, shall we? So we're going to let x bar equal 7.3, right? Because that's what it was in our example, right? 7.3 hours. Our n was equal to 81, and our sigma was equal to 0.6. All right. So let's do this, right? We wanted to figure out the appropriate interval for which to consider the appropriate range for ideoped battery lives, right? Given this sample, right? And I'm just gonna say consider a confidence level. And again, I'm going to use funky notation here. 1 minus alpha equals 0.95. You can just ignore the 1 minus alpha if you'd like. But I'm just going to say that, okay? So now let's go through the process here. We, I guess we should say, note that the standard error is going to equal 0.6 divided by the square root of 81. We can actually kind of do a bit better than that, right? We know that that's going to be 9. We know that 6 divided by 9 is 2/3. So this is going to be 6 divided by 90, I guess, right? Because 0.6 is 6 over 10. And 6 divided by 90 is 1/15th, I believe, right? Right, because 15 times 6 is 9. So I think we've actually got that. Now that said, maybe I should be a little bit nicer than that. 6 divided by 90. Okay. So 0.067 repeating. Okay, so there we go. So let's see now. Let's do this the long way and find the margin of error. So first off, we're going to go to Minitab and find the appropriate z-score. Let's see. Get out of this. Okay, so we go to graph, probability distribution plot, view probability, right? Same as before. But what we're going to do, actually, we're going to leave the mean standard deviation alone. View probability, we're going to do middle. And this is a little technical right here. If our confidence level is 95%, then we're going to do 1 minus that and then divide it by 2. Right? Because that's the amount of space remaining on either side, and that's what the middle asks for. And that gives us that z-score, 1.960. So I'll say using Minitab, z, I guess I'll just say z sub, I guess I'll just say z in this case. I don't want to get too complicated here. But z is going to equal 1.96. Now, you can also find this in your table in the book. So anyway, we have our z-score. Okay. So our margin of error is going to equal 1.96 times 0.067. Right? Maybe just to be clear where I got those numbers from, right? This is going to equal z times our standard error. Okay? And anyway, that's going to wind up equaling... Oh, I don't actually know. What are we going to get? 1.96 times 0.067. 1.132. Okay, we'll just say 1.13. Or just say 0.13. We'll just say 0.13. Okay. So we are 95% confident that the mean, IdeaPad battery life is within our 95% confidence interval. CI, which is 7.3 minus 0.13 to 7.3 plus 0.13, which equals 7.17 to 7.43. All right. So that's a good range for what we could expect the IdeaPad battery lives to be, based on our 81 sample size. All right, let's look at another example. IQ test given to 75 students. We have a sample mean. They're known to have a standard deviation, 90% confidence interval, right, of the mean IQ score. So what's the point estimate? Remember, point estimate is a fancy term for the sample mean value that you get, right? It's just that. Find the critical value, right? Well, for the 90% confidence interval, we're going to go to Minitab. We're going to say, okay, graph, probability distribution plot, probability, options, and we're going to keep middle. But because it's a 90% confidence interval, we're going to do this. And we get 1.645, right? Just note that that's that value, okay? 1.645. And you say 1.645. There you go. And then find the standard error. That's not so bad. The standard error is going to equal sigma over root n, which is 10 over square root of 75. Not the nicest numbers in the world. Let's calculate that, right? 10 divided by the square root of 75. 1.15, we'll say. Find the margin of error. So the margin of error is just going to be z times sigma, or times standard error, I should say, right? 1.645 times 1.15. Right, lovely. Let's just do that. 1.89. Okay. So the 90% confidence interval, let's make that 89 a little nicer. So the 90% confidence interval is going to be kind of a crude way to write it, but that's how we'll write it. 105.2 minus 1.89 to 105.2 plus 1.89. And, you know, if you have to leave it like that in an SLO quiz, then okay. But let's try to do a little bit better here, right? This is going to be 103 points. Is that 31? Am I getting that right? I think that's right. To 107.09? I have no idea. Let me try this. 105.2 minus 1.8. Yeah, 103.31, and then what's it? No, I meant to say plus. Yeah, I think I got that. Okay. My mental math isn't so bad, right? So anyway, that's what we get. Okay, so then the question is it likely that the population mean is greater than 100? Well, since 100 is greater than 100, since all of these values are greater than 100, I would say yes. Okay. Now, if all we need is the confidence interval, then we can use Minitab and just be very quick about this, right? Here, we've got another example, right? Random sample is very important, of course, that our samples are random. 100 freshmen, mean score is 458. Population standard deviation is sigma equals 116. They just say construct a 99% confidence interval. Okay? So what we can do for all this stuff right here is just Minitab it up. Right? We're just going to go here. I might need to go back to just remember stuff. We go stat, basic stats, one sample Z. That's a little different. Make sure to change this to summarize data. Our sample size was 100. Our sample mean was 458. Our known standard deviation was, I totally forget, 116. All right. And we're going to leave the options alone. And oh, look, it just... oh, wait. Never mind. Sorry, I have to do one thing that was different, right? They gave us a 95% confidence interval. I have to change one thing. Should have gone to options. Confidence level, my bad. Make that 99. Leave the alternative hypothesis alone. Now we do it. Now we have our 99% confidence interval, right? And that's... Actually, I wonder... Am I able to... No, I know. I don't want to copy and paste that. That leads to trouble if I remember correctly. right? So, yeah, we just kind of get that as our answer. Well, actually, do we have any room? No, we don't have any room. So I guess I have to kind of stick it here. But I'll just say that 99% CI equals 428.1 to 487.9. Okay, so that's what we get. Now they say, what if the sample size were 75 rather than 100? Would the margin of error be smaller or larger? Pause the video and think about it. The answer is larger, right? If our sample size is smaller, we don't have as much information, right? We're not as confident. We haven't sampled as many people. So our margin of error is going to be larger. All right, let's test it out, right? Let's make sure I'm correct, right? Go back into Minitab. Whoop. Stat, basic stats. We do this. 75. Sample mean is still 458. The standard deviation, 116. Options, make it 99. Right? See how that interval is a little bit bigger? That's because the margin of error is a little bit bigger. Right? But again, if we understand the concepts, then we should know this, okay? The confidence level were 95% rather than 99%. Would the margin of error be larger or smaller? Pause the video. The answer is smaller, right? We're not as confident, which means that we have to shrink our interval. So let's see. Is it likely that the mean is greater than 500? It's unlikely, since our interval is below 500. Okay. And that'll be it for this video.